So we're on site with the CLAMP system, or the Collaborative Lower Atmospheric Mobile Profiling System. And this is a mobile trailer-based platform that we use in the field. CLAMPS is made up of three main instruments. The first one is the Doppler LiDAR. The second one is the microwave radiometer, and the third one is the Atmospheric Emitted Radiance Interferometer, or ARRI for short. And I'll briefly talk to you about those three today. Here we have the microwave radiometer, which you can see coming out of the side of the trailer. The microwave radiometer is essentially a very sensitive detector. And what it does is it sits and it essentially listens to the ambient radiation coming from our atmosphere. And we record that information and use it to provide us profiles of temperature and moisture every few minutes. Here on the back end of the trailer, we see the enclosure that the ARRI stays in. And you can see this hatch that opens on the top, and that's what allows the ARRI to view the atmosphere. Similar to how the microwave radiometer works, the ARRI is also a very sensitive detector, measuring ambient radiance from our atmosphere. What's different is that the ARRI operates in a different part of the electromagnetic spectrum than the microwave radiometer. And that's important because using the microwave radiometer and the ARRI together provides us more information than either one can provide on their own. Also on the back end of the trailer, you can see the mast coming up off the corner. We use that to get surface meteorological variables like wind speed, wind direction, temperature, and humidity. Here inside the CLAMPS trailer, we have the Doppler LiDAR. This system actually lifts up and through the ceiling so that it can scan the atmosphere above us. The LiDAR sends out pulses of laser light, which reflects off of aerosol, small particles in the atmosphere. What we do is we can measure those aerosols and detect how quickly they're moving. And if we know how quickly the aerosol are moving, we know information about the winds in the atmosphere. So this system lets us collect profiles of horizontal and vertical motion in the atmosphere every few seconds. So what we normally do is we attach this trailer to a pickup truck and we take it to wherever we need to go to measure the phenomena we're interested in. These three instruments together give us information about wind, temperature, and moisture every few minutes. And all of that data streams in real time to this data system so we can see it. This type of system is really critical to some of the research we do here. We don't know a lot about what happens in the lowest few thousand feet of the atmosphere, where we live, where storms happen, all kinds of important phenomena. And it's hard for us to get measurements there because usually we have surface meteorology instruments like towers, or we release a weather balloon every few hours, or we have a radar that collects data maybe 1,000 feet above the ground, but we have nothing in between. A system like this one fills that data gap.
Today we're going to talk about NOAA's National Severe Storms Laboratory and some of the research that we do here at this lab. And one of the big tools that we use to do a lot of our field work is something called a mobile mesonet. And what that is basically a mobile weather station. Back in the early 90s in the original Vortex field project, which was designed to study tornadoes and try to understand how they work, they realized really early on that having a stationary tower or a stationary network of instruments makes it really difficult to study things like the weather that move. In order to accomplish those needs, we decided to put all of those instruments on a vehicle like the one that you see behind me and called it a mobile mesonet so that we can move with the weather and study it as it moves across the country. Let's take a closer look. So the observation rack that's on top of the mobile mesonet is kind of the key feature of this vehicle, and it's really what makes it a mobile weather station. This rack is specifically designed to take observations not only of the atmosphere, but to do so while we're moving, which means we don't have to stop and deploy anything or even just park the vehicle to take those observations. We can do all of these things while we're moving down the road, which is a really big advantage to collecting data against something that moves, like a severe weather event or a tornado or a hurricane, for example. And there's a lot of different components of that observational rack that we need in order to collect all of the data that we want. One of the first things is the pressure port. And the reason we have this kind of metal disc assembly on the front of the rack is actually to create a static pressure head. And what that means is that as the vehicle drives down the road, we don't want the wind speed from moving to actually cause any sort of pressure differences that we might see. We We want to try to measure what the atmosphere is actually doing. So that static pressure head allows us to remove those vehicle effects and that wind speed effect from those observations and to collect useful data. The instrument that you see on top is the wind monitor, and that measures wind speed and wind direction. And again, we can do that while we're moving. And the reason that works is we also have a GPS unit on the top of the rack. And we use the GPS unit to figure out how fast the vehicle is moving and in what direction we're traveling. And when we combine that data with the wind speed and wind direction data that we measure off that wind monitor, we can actually go back and derive what the ambient wind is without adding in the vehicle motion, which is a really, really useful tool. Now, driving down the road, you might think that it's very difficult to make a temperature observation or a humidity observation, and you would be right. There's a lot of influences that can make those observations incorrect or not mean what you think they're supposed to mean. So we have a temperature shield or a radiation shield that we use to house our temperature sensors and our relative humidity sensors that we can use to try to determine how much water vapor might be in the atmosphere or how hot the air is in the environment that we're trying to sample. And these are all really, really useful quantities. We also have an instrument called a flux gate compass. It's a magnetic field compass that gives us our vehicle heading when we're sitting still. We still have to know what direction the vehicle's pointing, and GPS units don't like it too much unless you're moving. So we use that to try to get our vehicle heading whenever we're stationary. And then finally, we also have a solar radiation sensor up on top, and that tells us how much the sun is shining and how much solar heating is hitting the ground. And this can be useful when you're looking at how hot the air is, because the sun is what drives a lot of that. So we use all of these tools to try to really understand what's going on at the surface inside severe weather or around it, or even just in an open field on a nice sunny day. It just depends on what the project is that we're trying to sample. The observational rack that we have on the front of the vehicle is being supported by this nice sturdy cage structure that we have over the front and rear of the vehicle. And that makes a nice supporting structure to hold all of that weight and equipment up there. But it also gives us another advantage, and that's the ability to put a hail cage over the top of the truck. When we do a lot of severe weather work, sometimes we encounter hail. And while most of them may be small, the bigger ones have a tendency to break windows and cause dents in the truck that we don't necessarily want. It's a safety issue. To avoid that, we have a hail cage over the top that's actually made from a steel mesh that shreds those hailstones or just completely blocks them from hitting the truck at all whenever they occur. So it allows us to do operations and take these measurements inside severe weather where you might be worried about damaging your car or breaking out a window. We can do those operations safely, and that's one of the key focuses of a lot of our missions, is collecting this data safely. So with all of this observational equipment on the outside of the vehicle, we need a lot of equipment on the inside of the vehicle to make it all work and to run it all. Now, one of the interesting things about this vehicle that most people aren't aware of is that it's actually a leased vehicle. We don't own it. We will have to turn it back in at some point when we're done with it, which means I need to find a way to install all of this equipment in a way that's safe, usable, but is also removable, because if I start drilling holes in things, it's not going to look too good when we go to turn this vehicle back in. So it is a challenge to try to put all this equipment in there, which usually means taking things out. Seats, cup holders, center consoles, all the things that you're used to having in your car at home, I have to remove so that we can put things like laptops, extra batteries, power systems, inverters, sounding systems, all the things that we need to be able to run those observations. Now, this vehicle is kind of designed with two stations in mind. The front station is where all of the observations from the mobile mesonet rack that we talked about actually come in and are recorded. Now, that laptop has a real-time display that allows us to view things like the last 5 minutes of temperature data or our current wind speed and wind direction. We can look at pressure traces or our location. There's even a view window that we can look at what our maximum wind speed is, and that's really useful for things like hurricanes. So it gives us a way to visualize all of this data in real time, and then we can communicate those observations back to the other people on our project, for example, and use this information as kind of a decision-making tool when we're doing operations in the field. The station in the back is very similar, except that it deals with the sounding system or a weather balloon. Now, that weather balloon system relays all of its data back in real time, and we can watch that data stream in and also use that to kind of inform our decision-making process when we're in the field. So together, these two systems operate everything that's in the vehicle and makes this vehicle a really powerful tool. So the final system we're going to talk about is the mobile sounding system, which is also located in the mobile mesonet vehicle. Now, this system is designed to give us a vertical profile of the atmosphere for things like temperature, pressure, wind speed, wind direction, and relative humidity. The same variables that we measure at the surface with the vehicle. Now, this is the same system that the National Weather Service uses all across the country twice a day to take those observations. But we can do it from a mobile standpoint rather than a fixed location, and that's really useful for studying severe weather events or things that move around. Now, in order to do that, we have to carry with us helium tanks so that we can fill up those weather balloons right on the side of the road. It takes about 2 to 3 minutes to fill one of those systems up. And once that balloon is filled and the instrument is attached, we can release it and actually continue moving and continue following the event. And that allows us to be very flexible and very nimble with these observations, which gives us a lot of ability to collect that data in really unique places such as severe weather events, tornadic storms, or even hurricanes, like the eye of a hurricane. The product that you saw today was a finished product, and obviously they don't come from the factory that way. There's a lot of work that goes into building these things and getting these vehicles ready for the field. So the work that you see going on behind me here in the National Weather Center, in the vehicle-based space that we have, is where we make all of those designs become a reality, where we put all of that equipment on the trucks, and we spend time putting the instruments on the racks and calibrating things and making sure that the data that we collect are as accurate as we can get it. If you want to know more about this tool or any of the other tools that we have available to study severe weather, please follow us on social media or visit our website. Thank you.
Hi, I'm Ted Mansell. I'm a research scientist here at the National Severe Storms Laboratory, and we're here to tell you a little bit about this vehicle behind me. This is the NOXP mobile radar. The NO stands for NOAA, the X stands for X-band, and the P stands for polarized or dual polarized. And this has been in service since 2009, and it's been used in a number of research experiments. Most importantly, it's been used for severe storms, but also winter weather. It's also been used to study bats and bird migrations. So it has a wide variety of uses. And if you look at the dish here, you can see there are 2 black pipes that go up there. And that's because it sends out 2 pulses at the same time. One is a horizontal polarization, and the other is a vertical polarization. And that gives us information about the shape of the objects that we're seeing up in the sky. And that's something that makes it very valuable for our weather research to understand what's going on inside thunderstorms. And next, Alan Zahari is going to show you more about the nuts and bolts behind how this radar actually works.
Hi, my name is Alan Zahari and I'm an electronics engineer. A team of engineers and technicians under my command built this radar many years ago at the National Severe Storms Laboratory. What we have here is a high-powered microwave transmitter. It operates in the X-band region. That's about 9 gigahertz frequency. The very short pulses of energy from this transmitter are transferred to the feed horn on the dish. As the antenna scans, this beam of energy encounters scatterers in the atmosphere, and the return signal from the scatterers are then digitized, stored, and presented to the operator who sits inside the cab in front of the monitors. The control center for this radar is in the rear side of this cab. Usually 2 meteorologists operate this radar. From here on the computer inside this cab, they can control all aspects of the operations, data collections, and then they can observe the scans in real time on their monitors and make decisions from there.
The information that we get from this radar can inform us about how well our weather models are doing in simulating these storms. Another thing that it measures is the wind. And if we have 1 or more radars, we can get a picture of the winds inside a storm. And that tells us about the evolution and how severe storms can form and evolve. Well, thanks for spending time with us and learning more about the NOXP research radar and the kinds of research that we do with it. And if you want to learn more, come to our website and find out how to contact us. Thanks a lot.